Yes, let's get started. My name is Maziar Raissi, Research Assistant Professor, Brown University. And currently I am at NVIDIA, a Senior Software Engineer. The guys above are not paying me anymore. So I've been here for about 11 months now. Everything started at Brown, and it started with this project supported by DARPA. And the project was design optimization of a supercavitating hydrofoil. Basically, the problem is you want to go as fast as possible so that you create vapor around the hydrofoils. And once you have vapor, that vessel is basically flying in water. There is going to be air around the hydrofoil. And everything ended with this project, where we have an aneurysm of a real patient. And we are learning the dynamics, basically the velocity and the pressure and the shear stresses on the wall of the aneurysm, given data that are coming from CT scan or 4D MRIs, space-time MRIs. I will go through basically the historical account of how things developed and where we are now. I'm not going to be talking about these three topics. I'm not going to be talking about classification, translation, or learning a high-dimensional probability distribution on the space of images. But there's a message here. The data dictates the model. If you have images and your task is a classification task, then probably a convolutional neural network that has a sparse structure is a proper tool. If you have a language task, probably a sequential model, like a recurrent neural network or LSTM. And these days, even convolutional neural networks might work for it. If you lack data that are labeled, you have unlabeled data, you can work with unlabeled data, learn the probability distribution, and generate images that look like reality. In scientific computing, we lack data. That's our problem. For instance, for designing that supercavitating hydrofoil, we don't have data. The data is going to be building that thing, the vessel, putting it in water, testing it, multiple rounds. That's not possible. The alternative is doing simulations. And this is what we did. We were using simulations. But simulations are expensive because these are Navier-Stokes equations. We have to do turbulence modeling. And they're expensive models. They take around 6 hours each round of the data generation and basically labeling your data. So at that time, we thought, this is our problem. We want to do design optimization of a supercavitating hydrofoil. That's the engineering look at it. We do a 2D cross-section. We get 17 or 18 parameters. We do our simulations, and we get lift-over drag. Now this is a function from a high-dimensional space to a low-dimensional space. We can put a surrogate here for our solver, basically. And we are looking for data efficiency. This is key. Data efficiency is a key concept today. We have started with Gaussian processes because they are data efficient. For a Gaussian process, the input is one of those high-dimensional shapes, xi, and yi is the lift-over drag. That's going to be our data coming out of simulations. Pairs of xi, yi. And we are going to be doing regression. With data, we are going to write a model for the data. And that's our model. We have a noise model that's normally distributed. If you write it in vector form, you get y is equal to f of x plus epsilon. Now, epsilon is high dimensional. It's basically your data. For prior, we say we are going to put a Gaussian process there. What is a Gaussian process? It's just a shorthand notation for this concept. Basically, you take any 2 points of that function, evaluate it, you get f of x prime. Those 2 points are correlated. They are normally distributed. And the distribution is given by this. Rather than writing this all the time, we are going to say f of x has mean 0 and this covariance function. The assumption is that if you have 2 points that are very far apart from each other, probably they are not affecting each other that much. This could be one assumption. And those assumptions, you can put them here in your kernel. That's exactly what I said right now. This is a covariance kernel that's going to do that for us. If 2 points are very far from each other, this exponential with the negative sign is going to make that go to 0. Therefore, they are not that much correlated. You can have multiple different kernels, but that's going to be the choice of your prior. This is a choice that you have to make. This is a choice that we had to make, this assumption. Once you make those assumptions, everything is normal. The data assumption was normal. Gaussianity is normal. Therefore, you can say my data is normally distributed with mean 0 and a covariance matrix this time. We are evaluating the covariance kernel at those points. And we are adding the noise. Now we have a likelihood. And once you have a likelihood, that's nice, because you can do maximum likelihood. Or you can do minimize the negative of the log of the likelihood that's coming out of the normal distribution. Normal distribution has an exponential term. The log is going to cancel that out, and that's the term you get. Why do we do that? Because we want to find the best kernel among all the kernels that we assumed. That's the purpose of training. Once the training is done, we have to do prediction or do inference. Somebody gives us a new point, x star, and tells us what is the value of that function at this point. Based on our assumptions and the data assumption, we can write down the correlation between that new point and the data. Once you have that, you can condition on the data. You get a mean, you get a variance. That's the mean. And this is the variance. So the beauty of Gaussian processes is that they are data efficient. Why? Because they are balancing the trade-off between data fit and model complexity during training time. Once the training is done, we get a nice uncertainty band around our predictions. So that's another advantage. We can do uncertainty quantification. Let's go back to our example where we were trying to do design optimization. This is the space, the design space. In our case, it was 17 or 18 dimensional. I'm projecting everything into a 1 dimension. And on the y-axis, we had our simulations. The blue curve, if we had it, that would be a luxury, because we knew what is the lift and drag for every possible scenario that could happen. But we don't have it. The blue curve, we don't have. This function, the blue one, we see it through observations, through data, which could be noisy. These are our simulations. Given this geometry, what is the lift over drag? Given that other geometry, what is lift over drag? We do a regression using Gaussian processes, and we get that. Basically, Gaussian processes, I want you to think of them as function approximators. During this talk, don't think of them as distributions. They are just function approximators. And if we go back to this slide, probably I shouldn't do it. This is just a linear combination of our kernel. If we expand it, if we call this alpha, it's going to be alpha times the kernel. Similar to the RBF. Yes?
Sorry, is this equivalent to kernel-rich regression, this formula?
Equivalent to what? Sorry,
Kernel-rich regression.
Probably. It's very close.
I guess it's equivalent if you take the...
It's equivalent to SVDs.
I mean, it is equivalent. That's the kernel-rich regression.
Yeah, exactly. It's basically RBF also. You can think of them as RBF kernels.
But it's equivalent if you're not doing averaging. If you just putting the maximum across the...
Yeah. This is equivalent, but usually this step is ignored. That's the contribution of machine learning. Among all of the possible basis functions, give me the best one. This is a very important round, the training round. So how do we use the uncertainty? We start with two simulations. One is here, one is here. We do a regression. The blue curve, remember, we don't know it. And that's a very bad prediction of the underlying function. But the uncertainty is telling us something. If we take the mean plus 2 standard deviation of the uncertainty, that's going to give us it's not the best one, an acquisition function. Now this guy we can optimize. We can query, what is your maximum? And it's going to tell us your maximum is here. We go ahead and sample at this point. We add another data. We run our simulation once. The function changes. The acquisition function is going to tell us go sample here. We are going to go sample there. The prediction is getting better. We are trying to find the maximum of the blue function through observations. And we are already very close. We had 4 observations, 1, 2, 3, 4. We keep doing that. In the next round, the algorithm is thinking maybe the maximum is somewhere else. Maybe the maximum is here, because there is huge uncertainty in the prediction. That step is called exploration. So we explore again, exploit. So we are balancing the trade-off between exploration and exploitation. For those of you who know the multi-armed bandit problem, this is close to that. Explore, exploit, explore, exploit, and we found the maximum. And we didn't need to run our simulations in this part of the domain. Now, if your underlying dimension is huge, this is really beneficial. We want to go even one step further. We want to become even more data efficient. We had 2 simulators. One was Reynolds average Navier-Stokes solver, which takes 6 hours per each simulation. And we had a potential flow solver, which takes 4 minutes. Can we somehow use that data, the low fidelity data? It's cheaper to obtain, but it's less accurate. We are going to write a model. We say the high fidelity, this is an assumption. This is a prior assumption that we have to make. We make a prior assumption that the high fidelity is a linear combination of the low fidelity plus some noise, plus some correction. And both of them are Gaussian processes, this guy and that guy. And I'm going to do this exercise. We are going to keep adding data on the low fidelity, basically running the cheaper solver without adding any data to the right side. And we keep adding data there. And I want you to focus on the right side. So the low fidelity data, along with Gaussian processes, along with some neural networks, helped us improve the already optimized design using genetic algorithm. That one is optimized using genetic algorithm, and we optimized it even further. There is no physics here. Everything is data-driven so far. We are being data efficient. We are doing our best. But when we were solving that problem, there is Navier-Stokes. There is physics. Can we somehow encode that physics inside the kernels? That was the question. Can we somehow physics inform our kernels?
Excuse me, I have a quick question. So if you go back to the slide where you show the multi-fidelity stuff, the previous slide. Yeah, so I guess I didn't really understand this. So how are you fitting a Gaussian process to a low fidelity model?
So the difference here is now you have two functions, low fidelity function, high fidelity function, and they are correlated. Any point on this function is going to affect a point on the other function. And we are leveraging that by conditioning on the already available data that you have on the low fidelity. Was that good? Can we physics inform? Let's say this is our physics, Berger's equation. ut plus ux, a coefficient uxs is equal to 0. We discretize, backward Euler, un minus 1 divided by delta t is the right-hand side. We approximate un by a Gaussian process. So here's the question. Why am I approximating un by a Gaussian process? Why not un minus 1? We had a choice to make. Put a prior here on un, or put a prior on un minus 1. If you put it on un minus 1, you have to solve a PDE. You have to integrate a partial differential equation. But if you put it on un, you can take derivatives. And taking derivatives is easier. And the whole talk of today is about derivatives. And we as human, not knowing that we are really good at taking derivatives. But we are. So let's leverage that. Here we are going to take derivatives and do symbolic derivatives, mathematical maple, nothing fancy. We can write down the correlation between un and un minus 1. This is the kernel that we started with. This is k. This is kn n minus 1. And look at the form. Compare it to the equation. Our equation is inside the kernel. K plus delta t, un minus 1, kx, coefficient kxx. So this is cool. Now, any sample that you generate at random from this distribution is going to satisfy this equation by construction. So how do we take the physics out? We take the physics out using data. Our data is our initial condition. Everything is data. The initial condition is a data. But we don't see the blue curve. We see the red dots. Some of them are really outliers. Given this data and boundary condition, we are going to train the hyperparameters of this Gaussian process. And the training is done using maximum likelihood. Basically, we are finding the best basis function among all those possible best prior. We find the best prior, then we do prediction into the future by conditioning on the data. You condition on the data, you do prediction. That's one step from time 0 to time delta t. So how do we continue from time delta t to 2 delta t? Should I take the kernel and do the derivation again? Make more derivatives out of the kernels? No, it's really costly. So we are going to summarize the information inside the data. What do I mean? Out of the posterior here, we're going to generate artificial data at some random locations. We can evaluate that function anywhere we want. The mean, we are going to use it to do prediction and do training. There is a variance here that we have to propagate. That's the only trick from time delta t to 2 delta t. And we keep doing that. We solve Berger's equation. We get the shock, and we get a nice uncertainty band around the solution. Any of these samples from this distribution could be a solution to the Berger's equation. So we are quantifying the uncertainty. The method is sort of honest. It's telling us any of these samples could be your solution. I'm not sure which one. The other day, I wrote down the math and compared. On one board, Kalman filter, which is a finite dimensional for ODEs. This one is for infinite dimensional PDEs. So we are not discretizing the space. There is one-to-one correspondence between the math. And Kalman filters are important. They took us to moon. This is happening in infinite dimensions. That was for a forward solver. Basically, I give you initial and boundary conditions. Give me the solution. Now, can we do inverse problem? If I give you data, even inside the domain, can you tell me what are the parameters of the PDE? That's an inverse problem. Now we have more data, and we have more unknown. Let's go through the math real quick. We discretize, put a Gaussian process on UN, push it through the differential equation. That's a physics-informed prior. So nothing changed, except for one thing. The parameters of the differential equation, lambda 1, lambda 2, lambda 3, turn into hyperparameters of this kernel. The same maximum likelihood methodology that we used to do training and find the best thetas, we are going to use the same methodology and find what is lambda 1, lambda 2, and lambda 3. So the cost of this is the cost of a forward solver. And you do inverse. And it's very data efficient for two reasons. One is that Gaussian processes are data efficient. We have nothing to do with it. The other one is, this is a physics-informed prior. We are putting a lot of structure on this prior. That's why, given the chaotic dynamics of Kuromoto-Sivashinsky equation, we can use only two snapshots in time that are delta t apart and find out what are the parameters, even in the presence of noise. Chaotic system, very little data, and noise being added. Chaotic system, very little data with noise. And that's the noise on the data. That's basically the data that we are using. You can do Navier-Stokes, flow past the cylinder, 2 snapshots of this one, not the whole time series, not the entire spatial-temporal time series, 2 snapshots. And we are learning the coefficients in front of the, basically what is the Reynolds number. And the Reynolds number corresponds to the shape of the object in front of us. Like what is the size of the object, given the flow pattern behind the cylinder. And that's basically a real experiment that we tried to do, and we failed. This is real data. We failed, not because the method cannot do it, but because the data had gravity inside it. And we were not modeling gravity at the time. So far, Gaussian processes, a machine learning framework, is helping us do scientific computing. Can we help Gaussian processes back? Gaussian processes are not scalable to big data because you have to invert that covariance matrix. It's a full covariance matrix. If you have, that's the size of data cubed. That's the cost of it. The idea is, OK, you have this big data set. Maybe most of this data is redundant. Can you do data reduction? What if you have millions of data? What if 10 of them are just important, are informative? It's similar to high dimensional, not all high dimensions being important, but some of them being important, a low dimensional manifold. Maybe not all of the data is important. Some of them are more important than others. Can we find those? And the idea is coming from Gaussian processes itself. Gaussian processes has this prior, gives you the posterior. Now the idea is the posterior could be your new prior. Condition on that, get a new posterior, that's your new prior, and keep doing that. But keep conditioning on mini batches of data. And keep updating these red circles. Basically, we are summarizing this big data set into 8 hypothetical data set. And this idea is coming out of numerical Gaussian processes, where we had to generate artificial data out of our posterior. Same idea. And it's an idea that makes sense. This is how humans think. We start with a prior, uninformative prior. Then some data comes in. We condition on the data. We update our prior. Then some other observations come in. We update our prior about the world. That's what's happening here. Where did we apply it? This is Cape Cod area near Boston. And we applied it on satellite images. And satellite images are spatio-temporal data sets. And what are we measuring? This is the sea surface temperature. Some days are cloudy, so you have very few observations. Some days are sunny, you have a lot of observations. Some days are partly cloudy. And whenever you have a spatio-temporal time series, that's huge data. That's big data. So a Gaussian process cannot do it. We have to summarize the data. And we summarize the data set into 1,000 data points. And that was enough to give us a mean prediction and uncertainty prediction. And the uncertainty is nice. It makes sense. It's going down here where we had some data. So the first part is over. I hope I didn't tire you. The next one is about neural networks. Can we do the same thing using neural networks? Can we physics inform neural networks? For Gaussian processes, we were using symbolic differentiation, basically mathematical, Maple. The only reason, I mean, one of the major reasons neural networks are successful is because of automatic differentiation. So we are good at taking derivatives, we as human. Let's leverage that. But let's start with the concept of regression. It's similar to before. The data is the same as before. This one is familiar. If you have a function, you can write it as a linear combination of some basis. This is what we do in scientific computing all the time. We write basis. But what if you can learn the basis? Without this guy, it's going to be boring. Our basis is a linear combination of another basis. Then it's going to be linear. Everything is linear. It's going to be boring. We put a nonlinearity here to introduce nonlinearity. It doesn't have to be tanh. It could be ReLU. It could be Swish activation function. You name it. You can get creative. Then what is HL minus 1? A linear combination of another set of basis functions. Dot, dot, dot. H1 is a nonlinearity applied on a linear combination of another, of the input, actually. For Gaussian processes, everything was about the covariance. For neural networks, everything is about the mean. That's coming out of our noise assumption. That's our noise model. That's our likelihood model. Now we can write down our likelihood. That's the likelihood. That's another form of the likelihood. Basically, it's just mean squared error. So mean squared error is sort of like likelihood, where you ignore the noise, when you don't optimize over the noise. Prediction, do you remember, for Gaussian processes was tough. We had to condition on the data. We had to carry the data with us all the time. With neural networks, we are summarizing the data in these parameters. Therefore, prediction is easy once you train the parameters. And it's fast, and it's efficient. Gaussian processes versus neural networks. Gaussian processes are non-parametric. What do I mean? You have to carry your data with you all the time. You have to condition on the data. Neural networks are parametric, and these are the parameters. Gaussian processes do not scale to big data because you have to invert that matrix. Neural networks are scalable. Why? Because you don't have to do your summation over all of your data. You can do mini batching to get an approximation of your gradients to do training. Gaussian processes quantify uncertainty. Neural networks don't. Gaussian processes balance the trade-off between data fit and model complexity. Neural networks, no. Neural networks can overfit, unless you do regularization of different kinds. So these are the two extremes of this story. You can mitigate the differences, like scale Gaussian processes to big data sets. We saw an example. But you have to work harder. It's against their nature. You can encode uncertainty into neural networks, like dropout, but you have to work harder. Let's physics inform neural networks. We are going to approximate our function with a neural network. It has a bunch of weights and biases, and we use automatic differentiation to take derivative with respect to time, x, xx, and you get your residual. So our contribution is not coming up with automatic differentiation. It has been around for a while. Our contribution is the way we are using it to obtain a neural network that knows about the physics, that knows the equation. This neural network F has the same parameters as neural network U, same weights and biases. And we do training this way. Paris went through a nice way of doing the training better. But this is the benchmark. Let's go with that. This is pins. And we can solve PDEs. That's one angle. You can solve PDEs, but we know better ways of solving PDEs. Like finite differencing is a very good one. Finite elements has been around for half a century. Spectral elements, that's very efficient. Finite volume, in the industry they're using it all the time. And it's fast, efficient. Okay, we can solve PDEs using neural networks, that's cool. The other angle is that we can train a neural network using 100 data sets. This is data efficiency from the machine learning perspective. Because we are regularizing our neural networks heavily with the physics. That's the more exciting story that I like. Making neural networks data efficient.
How about a high-dimensional differential equation? Suppose the dimension is like 1,000, then how many do you think?
It's coming up. That's a very good question. The question is about high-dimensional PDEs. But let's go through the cost of physics-informed neural networks. What is the cost? This is Schrödinger equation. Nothing special about Schrödinger equation. It has a real part, it has an imaginary part. So we are going to put a neural network here. Up until this part, this is physics uninformed, the most boring possible type of neural network. Fully connected. 10 layers deep. Let's say 50 layers, 50 neurons. Let's look at 10 layers. We are going to go and apply automatic differentiation once. We take the derivative of this guy with respect to time. And we are going to do back propagation. When you do back propagation, you're literally copying the adjoint of this guy and putting it here. So we just doubled the length of the network. We go and take the derivative twice. We just doubled the length of the already doubled network another time. So it's going to become 40. That's the cost. You create a computational graph. It's going to be a huge computational graph, and it's going to be very deep. So these are really deep networks. These operations are non-trivial operations. And then you write down your residual. So up until this point, we are not committing any errors. It's machine precision accurate, whatever we did. Your machine precision could be float 32, 10 to the power negative 7, but we committed no errors up until this point. Where do we commit errors? We commit errors here. And this is what Paris was talking about. This is very important. Properly weighting these is literally open for research. It's open territory. And you can solve Schrödinger equation. That's the absolute value of the solution. So I get this question a lot. What is the difference between, how do you compare pins with finite elements, finite volumes, finite differences? How do you compare it with reduced order models? Let's compare it line by line. Let's say you want to do finite elements. You have an infinite dimensional space of your solution, and we have to find the finite dimensional representation in that high dimensional space. We are going to choose basis. With neural networks, we are going to choose a bunch of, with pins, we are going to choose a bunch of neural networks to represent this space. With reduced order models, we choose them smartly, like based on previous examples, based on previous time, based on similar geometries. We choose a basis. Differential operators, finite elements, writes the weak form. Finite differences, discretizing it. Pins use automatic differentiation, machine precision. So we didn't touch our operator. Reduced order models, similar as finite element, finite volume model. For our solver, we use a linear solver, or we use a nonlinear solver, or we use iterative solvers. Here we are using gradient descent to do training. This is an optimization now. Similar for reduced order models. For evaluation, we do interpolation, we do inference, we do interpolation. That's how you can compare pins as a forward solver with the landscape. So they are not efficient, pins. They're slow. Compared to finite volume, they're slow because of the training procedure, because we don't want to hide the training round. You can go to high dimensional. You can solve high dimensional PDEs. You can do high dimensional Hamilton-Jacobi-Bellman equation. You can do high dimensional Black-Scholes equations. And this is where we start to gain that advantage with pins. Why is that? With finite differencing, if you have a one-dimensional space, you can put 10 points in your grid. In two dimensions, you do 10 squared, 100. In 3 dimensions, 10 cubed points. 10 to the power 4, 5, it's out of the possibilities. Mm-hmm. That's the curse of dimensionality. With neural networks, we don't have to worry about the curse of dimensionality because our degrees of freedom is not tied to the space. Our degrees of freedom are something abstract, the weights and biases. This is an abstract concept. And they appear in all places. Like if you have 100 assets, what is the price of an option on these 100 assets? 100 is the dimension of your problem. This is where we start gaining advantages. Another place is when we do inverse problems. Let's say we are collecting data behind the cylinder, and we want to learn the Reynolds number. These two parameters, lambda 1, lambda 2, are going to be added to 10,000 other parameters of the neural network. And we're going to train them using mean squared error. That's fine. To be honest, when we were writing this paper, we were trying to find these parameters. What is the Reynolds number? And the algorithm gave us that. This is OK. It gave us something more. It gave us the pressure without even having a single data on the pressure. The pressure is popping out of the continuity equation through optimization. It's coming out of the physics. Can we do real stuff with it? And at that time, we had this idea. What if we inject particles in somebody's arteries? We track those particles and get the pressure drop and diagnose whether somebody has a heart stenosis or no. And the stenosis is like this. Whether the doctor has to do a surgery or no without opening the patient up. But that's a very stupid idea. It worked. We got the pressure drop. It's a very bad idea because you cannot inject particles in somebody's arteries. That guy is going to die. But people do 4D MRIs all the time. They inject concentration in our arteries all the time to do imaging. bolus dye. They do it all the time. They can use the oxygen level of our blood to do 4D MRI. This is when we started experimenting with concentration data. This is a passive scalar. It's just being advected by the flow. It has no effects on the flow. And we were able to get the velocity and the pressure, where we had different Peclet numbers. Peclet number is basically how diffusive is that dye that's being injected in our body. That's cool. Can we get a little bit more real? So what's the problem here? We had a neural network. We had observations only on that part, 5. So we had observations only on this guy. So you cannot do a regression on it and get these guys out unless you enforce the physics. And this is how we enforce the physics, using automatic differentiation. This is our hidden physics. And ideas like Markov, hidden Markov models are coming into place. But everything is in infinite dimensions. The loss is boring. There is room for improvement here. That's the data. That's literally the data. A spatiotemporal time series. And we are cutting the data here. We are not enforcing boundary conditions. And with PDEs, boundary conditions are important. Without boundary conditions, you don't have a solution. It's not unique. We are not enforcing initial conditions. PDEs without initial conditions are not solvable. If you cut an artery from here, what is the proper pressure boundary condition? There are ad hoc models for it, but nobody knows. Because you are cutting this part from the whole arterial system of a human body. Given that data, you can learn what is the flow like, and given the equations, learn the trajectories, and the pressure, and the shear stress. Everything is in the paper. You can do fluid structure interactions, get lift and drag forces, and the damping and the stiffness of the solid. You can couple ODEs and PDEs, like particles, the Eulerian and Lagrangian framework, and get the Lagrangian one out. You can do turbulence. This is the PDF of the concentration. And from the PDF of the concentration, you can learn the conditional diffusion. And conditional diffusion is hard. Conditional stuff are tough to get. I'm not an expert in turbulence, but Peyman is. And once he saw these results, he was really happy because it took him pages of rigorous mathematics, like derivations, to come up with a solution to this problem. You can learn dynamical systems by putting a neural network on F and learning it using a loss function that's coming out of this ODE. You can learn infinite dimensional dynamical systems. You can learn PDEs. Basically, you are collecting data from here to here. You learn the dynamics, you extrapolate. Something cool. You can change your initial condition and let it solve it. That's KdV equation. And thank you.